So, welcome everyone. Thank you for joining us this afternoon. Today we have the fortune of having Charles Margossian from the Flatiron Institute. He's a rising star in computational statistics and Bayesian methodologies. And today he's going to talk to us about Margossian Monte Carlo in the AI area, AI era. So thank you very much, Charles. The floor is yours.
Thanks for the introduction. So a year and a half ago, I was teaching at the summer school on advanced Bayesian methods in Leuven, which is a wonderful historic town in Belgium. And one of the students asked a very elementary but profound question, which was, when I do inference, for how long should I run my algorithm? And this was my answer. You may recognize this from the final chapter of the Count of Monte Cristo. And it's a cheeky answer because actually, as someone who does algorithm development and also who builds probabilistic software, this is exactly the sentiment I want to safeguard the scientists from having. We don't want scientists to wait. We want them to use fast algorithms, and we don't want them to rely on hope. We want them to rely on theoretical guarantees, or when these are not available, heuristics or diagnostics that are theoretically well motivated. And today I want to talk about how parallel computation helps us achieve the dual goal of building algorithms that are both fast and reliable. And the reason I want to talk about parallel computation is that if you look at Moore's law, which tells you that our compute power is growing exponentially, for the past decade, that has no longer been true for single-thread units. But it is true for processors that do parallelization. And now you might expect that better computation makes your algorithm faster, but I'm going to try and characterize how much faster and also talk about some persistent bottlenecks. And on the theme of reliability, I'm first going to show how parallelization can help us build better diagnostics, but also look at some ML algorithms out there that already leverage parallel computation and ask what are some theoretical guarantees that we have for those. So the outline is as follows. I'll first talk about probabilistic modeling to provide some motivation, some demonstration of applied work. Then we'll talk about Markov chain Monte Carlo, in particular this idea of using a lot of chains in parallel, and I'll present a convergence diagnostics for this many short chain regime. And then we'll talk about variational inference, which already uses parallelization, but lacks some of the theoretical guarantees that MCMC and more classical statistical methods have. So I'll present a positive result showing that VI is very good at learning symmetries, and we'll see what the implications of that are, but also a negative result in the form of an impossibility theorem. Let's see, is there a way of removing the... Okay. All right. So when I think about probabilistic models, really our goal is to describe complex data generating processes. And I'll give an example from a collaboration with epidemiologists in Switzerland, which was one of the first studies of COVID-19. So you go to the epidemiologist, and this is the model they gave you of how the disease propagates in a population. It's an SEIR model. And really what it is, it's a system of differential equation. And if you solve it, you know how much of your population is infected. What this is not is a data generative process, because actually none of the quantities that appear in this differential equation are going to be observed. Rather, our data looks a little bit like that. What we're observing is reported cases and reported deaths. So if we look at reported cases, to actually get to the reported cases, first I have to look at how many individuals are infected. Amongst those individuals, how many of them have symptoms? And then amongst the people with symptoms, how many get tested? And you may remember that at the beginning of 2020, the number of tests available was not that large. So people were really prioritizing people with severe symptoms. So what the data generative process does is it builds on top of the scientific model to try and account for these random processes that lead to the observations that we have. And specifically, we're going to specify a joint distribution between observed quantities, so here reported cases and reported hospital deaths, and unobserved quantities, which include infection rates and DCR, the number of individuals with actually symptoms, and we'll also try and make some predictions, for example, estimating the mortality rate. In your model, there's going to be a joint distribution over all the observed quantities and the unobserved quantities, right? Specifically, that joint distribution can be broken down into a likelihood term and a prior term if you are in a Bayesian setting. Right? And then we'll reverse engineer the data generating process to compute a posterior distribution, right? That's the task of inference that we're trying to solve. And now just to motivate a little bit why I'm doing this in a Bayesian setting, well, first of all, I want to have access to priors. So if I look at something like the symptomatic rate, there's nothing in the data that is going to tell me what the symptomatic rate is. Because I know who the people that are getting tested are, but I have no idea about the people who are not getting tested. And if you don't have the symptomatic rate, you're not going to be able to estimate interesting quantities such as the mortality rate. So what we ended up doing for this particular study is there was a cruise ship in the coast of Japan called the Diamond Princess, and they realized that individuals had been infected. So they tested the entire population of the ship, regardless of whether people had symptoms or not. And based on that, you can get an estimate of the symptomatic rate. But it's a fairly small data set. So we're not going to fix the symptomatic rate. We're going to use this to build a prior distribution. And then the Bayesian machinery allows us to propagate uncertainty into all our predictions, right? You can imagine how for this kind of critical task, you would want to have some good uncertainty quantification. Because you don't just want to predict the most likely scenario, you also care about worst case scenarios when you're talking to policymakers. So how did we actually implement this? Well, it turns out the epidemiologists did a lot of the work because they had access to what's called a probabilistic programming language. And here I'm pointing out STAN. This is actually not the code we used for this particular model. This is a simpler code for a simpler epidemiology model that I use when I teach STAN. But you can see how it already has a lot of the ingredients that we need, right? So up there, we're solving a differential equation, right? That's our SEIR model. Then we're specifying our priors and our likelihood. And these languages are very expressive and they allow scientists to compose probabilistic models. Right? In other words, specify a joint distribution. And now the idea behind those languages is you push a button and you get an approximation of your posterior without the scientist having to design an algorithm that's specific to their model. Right? So this sounds quite a bit idealistic, but this is what we use for the COVID-19 model. And actually, STAN has an estimated tens of thousands of users. Right? So this is something that does empower scientists. Nonetheless, one drawback is that these estimations of the posterior tend to be quite expensive. And the main reason is that in order to get approximations of the posterior, you need to compute gradients of the log density many, many, many times. Right? So the cost of computing one gradient and the number of times you need to compute the gradients drives your computational cost. So I'll speak only very briefly about gradient computation. So first of all, notice that the user is not asked to specify the gradient. This is done automatically, and it's done with something called automatic differentiation. So I didn't invent automatic differentiation, but I did write a review that was very favorably received. And automatic differentiation drives all of computational statistics and machine learning. You need those gradients to get those algorithms that scale well in high dimensions. It's important that you implement those well. I'll just give you an anecdote that for this ODE-based model, the way in which we parameterized the differential equation had a huge impact on the differentiation cost. And we actually got a model which was running in 3 days to only run in 2 hours. And from that, not only do we have a model that runs quickly, we're able to now try other models, complexify the model, and go to more interesting models. Now, I've been a STAN developer for 8 years. That's why I bring STAN. But there are a lot of great probabilistic programming languages out there. The things I'm going to talk about apply broadly, and you do apply them to different applications. So this is an example of the collaborations I've had with scientists in biomedicine, in astrophysics, in machine learning. And today I want to talk a little bit more about what I consider the next generation of probabilistic programming languages, in particular TensorFlow probability, which is something I started looking at with a team at Google Research. And really, we came together thinking, Stan is wonderful. What is the next generation of probabilistic programming languages going to look like? And the main thing we had in mind is the hardware has shifted. We went from what was 10 years ago a mostly CPU-based world to a world that is based on GPUs. So we have a hardware shift, and our software needs to reflect this. And GPUs, I'll just say briefly, they're very, very good at performing the same operation many times in parallel. And what I want to argue today is that this hardware shift is not just a shift for the software engineers, it's also a shift for the researchers who develop methods, develop algorithms, and also analyze these methods. I will show you how the theory changes when we think in a GPU-based world as opposed to a CPU-based. So with that, I'll jump into Markov chain Monte Carlo. So I said we're interested in estimating a posterior distribution, and typically what that means is there are some summary quantities that we want to estimate, and these tend to take the form of expectation values, right? So expectation values fully define a probability distribution. For example, we might be interested in the mean and in the variance to quantify uncertainty. And the idea behind Monte Carlo methods is we're going to do a sample estimation of these expectation values. Now, if I want to understand how well my Monte Carlo method is performing, I simply look at the expected squared error of my Monte Carlo method, which is going to decompose into a squared bias and a variance. And that decomposition is interesting because actually the two kinds of errors have two different sources. I have a bias because in practice, I usually don't have access to samples from the target distribution. That's the case in a Bayesian analysis. So that's going to incur a bias. And I have a variance, mostly because I'm using a finite number of samples, right? And not only that, these samples tend to be autocorrelated. And if you look at the implementation of MCMC, the design reflects those two sources of error, where I'll first have what's called a warm-up or burning phase, where I start from some initial distribution P naught, then I repeatedly apply a transition kernel, and as I do, I get closer to my target distribution. In fact, asymptotically, you will get to your target distribution. In practice, you get close enough, but then even once you're close enough, that's not sufficient, because you have the variance term that you need to kill, and so then you start accumulating samples during what's called a sampling phase. So I discard the initial warm-up phase because it's biased by my initialization, and then I keep the sampling phase. And one thing you might notice is that in my sketch, I have made the warm-up phase shorter than the sampling phase. And that's because very often, the variance decreases at a slower rate than the bias. Right? So one example is when you're in a scenario called geometric ergodicity, which is not too uncommon actually, your bias decreases at an exponential rate, whereas your variance at best decreases linearly if you're able to draw independent samples. And we don't even draw independent samples. But here's the good news. I have two ways of killing the variance. And I think you see where I'm going here. I can either run longer chains, or I can run more chains. Now, I cannot do that to kill the bias. I can average out variance. I can't average out bias. But even then, if I were to completely trade the length of the sampling phase with the number of chains, I would be able to go from an error that decreases linearly to one that decreases exponentially. And the good news is that we now have the technology to actually efficiently run hundreds of thousands of Markov chains in parallel. There are some engineering challenges that had to be overcome, but this technology exists. You can open a Google Colab, run TensorFlow probability, and pretty seamlessly run 1,000 Markov chains in parallel in a very efficient manner. And once you have access to that technology, the regime of MCMC changes. And this is called the many short chain regime of MCMC, where now I've made my sampling phase arbitrarily short. And now my warm-up phase is much longer. So now I want to go back to the question I asked at the beginning, which is for how long should I run my inference algorithm, and specifically for MCMC, for how many iterations should I run MCMC? And this is a difficult question. And what I'll say is that traditionally, the answer you get from people is, well, you run it until your variance is small enough, or until your effective sample size is large enough. I literally had that conversation yesterday in the math department with the statistics group, where the answer was, oh, until we have effective sample size corresponds to variance. Well, in the age of parallel computation, what dominates my computation is no longer variance, it's bias. The bias is the thing that I need to kill. And the reason why people almost exclusively worry about variance was because in traditional MCMC, it decays much more slowly than the bias. And so by the time your bias is controlled, your variance is controlled, your bias becomes negligible. In fact, you may have heard this idea that MCMC is an unbiased method. It isn't. So now I want to go back to this question for how long should I run my MCMC? Well, what I would suggest is that the number of chains is what kills your variance. So for each effectively independent sample that you want, you run one chain. Your sampling phase, well, one iteration, maybe a few. And now the question is, what should be the number of warm-up iterations? Because this is now what dominates my computation and what dominates my error. So there's actually literature on the topic. There's literature that specifically tries to control the bias. I'm not going to talk about this today. I just want to acknowledge it. What I'll say is that it can be difficult to implement in practice in a general purpose way that would serve the broad scientific community that uses probabilistic programming. But that work exists. I think it's exciting, and I think it does have a lot of potential. The method that people actually use in practice comes from the idea that your bias comes from your initialization. So you're going to track the influence of the initialization. And if your Markov chain forgets your initialization, you can somewhat safely conclude that you've overcome your bias. And this was the idea behind this R-hat statistics, or Gell-Mann-Rubin statistic. And the idea is you run multiple chains that each start at very different locations. And then you see whether the chains, despite their different initializations, are in agreement with one another. And so there are different ways to compare the chains. One of them is to say, you look at the mean of each chain, and then you look at the variance between those means. You see whether they're in good agreement. But there are objections to this method, and one of them was actually raised in a recent paper by Vatsan-Natsons, who pointed out that really all you're doing is you're looking at the variance of your Monte Carlo estimate. How could you possibly learn something about the bias, right? And remember, that's what I'm trying to kill. So that's the first paradox. And then the other thing that my colleagues and I pointed out is that if all of my chains are very, very short, have a very short sampling phase, well, that variance is always going to be large. And the only way you're going to kill that variance and get R-hat to diagnose convergence is by running a long sampling phase. And so people would be running a lot of chains, but then they would also be running very long sampling phases. So they're not getting any of the computational speed up because they don't have any reliable diagnostics to tell them that they're converging. So the way we solved this problem was with something called the nested R-hat. And to motivate it, I'm going to go back to my error decomposition. Well, anyways, look at the next line, right? And here what I've done actually is I've further decomposed the variance using a law of total variance. Right? And I want to highlight this first term, which I'm going to call the non-stationary variance. And really what it is first I have an expectation value, a conditional expectation value, where I have condition on my initialization. So I'm recognizing that I depend on my initialization. And then I look at a variance term that comes from how much variance there is in my initial distribution. Now, if I've run my Markov chain for long enough, then I've forgotten my initialization, my expectation value doesn't depend on my initialization, and this conditional, this variance of a conditional expectation goes to 0. So this is actually a very appealing way to track the initialization. Okay. On the other hand, I have this other term, which is called the persistent variance. And the reason why we call it the persistent variance is that even if you're stationary and you have forgotten your initialization, you still have a variance due to the fact you have a finite number of samples. So the reason why R hat is an interesting quantity for checking if your warm-up is long enough is because inside your variance, there is this non-stationary variance term. But the problem is that it gets contaminated by this persistent variance term. So is there a way to construct an estimator of the non-stationary variance without worrying about the persistent variance? And the strategy to do this is to create these superchains. And within a superchain, so these superchains are really groups of chains constrained to start at the same point and then run independently. So actually, each superchain, if you're doing a lot of chains in parallel, will have a lot of samples, so that will kill your persistent variance. But because they're constrained to start at the same point, you're still tracking the initialization. And very concretely, if I look at the error decomposition of the superchain, what I have is the same bias, the same non-stationary variance, but now a persistent variance term that I'm able to kill with the number of chains, which means that I have a consistent estimator of the non-stationary variance that I can now use to check whether I've warmed up long enough. And let me highlight something about this consistency result. This is not a traditional MCMC consistency result, in the sense that the asymptotic limit is not taken along the length of the chain, which is what you see in most theoretical papers about MCMC. It's taken along the number of chains. Okay. So the asymptotics actually reflect the shift in hardware and allow us to work with non-stationary Markov chains. All these terms, the bias, the non-stationary variance, if you're doing asymptotics along the length of the chains, you're completely going to miss them. So let me quickly demonstrate this diagnostic in action. So I'm going to run 2,000 chains broken up into 16 superchains. I'll put my money where my mouth is, sampling phase of length 1. And then I'm going to try different warm-up lengths. So some of these warm-up lengths are way too short, but I want to make sure that my diagnostic tells me that they're too short, and some of them will be sufficiently long. And then I'm going to compute nested error hat and the error across multiple dimensions. So this is what these results look like. This is from a pharmacokinetic example. Again, it's a model with a differential equation, a hierarchical prior. This is, this is not a toy model. This is a model we care about, that scientists want to solve. What I have here is my nested error hat. As it approaches 1, then it indicates convergence. And then you can do some calculations to estimate what is the squared error I would get if I were able to draw exact samples from the posterior distribution. Right? So in a sense, when you've converged, you kind of want all your error to concentrate within that interval. And you can see that when the error in my Monte Carlo estimator does concentrate in my interval, this corresponds to when my nested error hat is small. On the other hand, if I have a large nested error hat, I am indeed warned that my Monte Carlo error is too large, which means I need to run this fast. And this works for a bunch of models. So here across finance, social sciences. Does anyone have any idea what's going on here with the last example at the bottom right, which is a bimodal target distribution? Yes.
Presumably you need the MCMC chain to switch between the modes before you get a good idea of their relative height.
Yes, yes. And you, same thought? Yes, thank you. Yes, so what's going on is that right now the MCMC algorithm that I'm using doesn't do a good job jumping between modes. And what it means is that the initial point determines which mode I end up living. And moreover, I'm not forgetting my initial point. And so even after I run a long warm-up phase, I'm not forgetting my initialization, and so my error stays large. And so for all these experiments, I both have a large error, but I also have a nested error hat that's warning me that my inference is not reliable. Oops. Okay, so to kind of conclude our section on MCMC, I want to highlight some open questions. So first of all, I've presented this non-stationary variance as a useful quantity to track, to determine the length of the warm-up. This is something we've demonstrated empirically. We have some theoretical justification. We also have some analytical example where you can show that the non-stationary variance decreases at the same exponential rate as the squared bias. So it stands to reason that it's a good proxy plot, but I want to work with some theorists to try and get some stronger theoretical guarantees on how well the non-stationary variance tracks the squared bias in general settings. There's an immense wealth of theory on reducing the effective sample size, reducing the autocorrelation of stationary Markov chains. We need to move to non-stationary chains and find ways to adapt the wealth of theory to this non-stationary regime, which is pertinent to the age of GPUs. And then really the grail of this is, instead of, you run your algorithm and then you check, having a way to continuously check your samples so that you can automatically stop your warm-up, and then you draw your short sampling iteration and you're done. So we want to find a way to adaptively set the length of your Markov chains in a near optimal way, right? And so there are a few challenges to do that, but this is what we want to put in the hands of the scientists to analyze it. Any brief questions about MCMC before I move on to the second part of the talk? Yes?
Yeah, just on going back to that point, I was already thinking of asking this. So are these methods helpful when you have complex distributions with multimodality?
Yes. And maybe it depends on what you mean by these methods.
Well, having lots of short chains.
Okay, good. So I was going to say the nested R hat is helpful because it lets you diagnose when standard MCMC is not able to jump between those. Now, there are algorithms that use a lot of chains and lets them communicate with one another in order to propose global proposals that then allow you to jump between worlds, right? So the work I'm most familiar with is the one that Marie-Lou Gabriel from the École Normale Supérieure did. And in order to train these global proposals, you already need a lot of chains. And kind of the conversation that we had is I said, well, by the time you've trained your global proposal, you probably don't need to run a long sampling phase at all. So you have these methods, and I think that, the connection is not immediate, but it can be made if you think about methods like sequential Monte Carlo, where you have a lot of particles and you get them to communicate with one another. These are methods that do use a lot of chains. So there are actually benefits to running a lot of chains, which can help to some extent in multimodal problems. Let's say if you don't have an exponentially growing number, right? So I can't promise you're going to sample from the posterior Bayesian neural networks. But by the way, these are examples where actually you're leveraging the parallelization and the ability to run a lot of chains to also reduce the bias more quickly. What do you think about that? Okay, one more question, and let's keep them brief. And I promise that at the end we'll have time to return to.
This might be too long, it might be too much. But so I'm right in thinking the super chaining is beneficial because it helps you evaluate that conditional expectation.
Yes.
But the drawback is you sometimes you reduce the number of independent starting points.
Yes.
Which is what leads to the bimodal. I wonder whether there's a sort of alternative approach where you just have 2048 different starting points if you estimate that conditional expectation with like a regression-based method or something.
So there might be. So there's an interesting question. So first of all, there's an interesting question of how much distinct initialization is weighted, right? And there's a bit of a trade-off. If I give you a total number of chains, you have to decide within that total number of chains, what is the partition that I'm going to? And actually in our paper, we have an analysis that tells you need to balance having enough initialization and having large enough superchains to kill off the persistent variance. right? And what I will say is that it turns out that as long as you're not too extreme one way or the other, there are a lot of different regimes that work. And in practice, I don't think you need too many highly distinct initializations, unless you're in a problem where you know that that's going to be a subject. On the topic of not constraining the things to start at the same initialization, I'm interested, and let's talk about that after. So I'll continue, but again, I'm here all day, and we'll have time at the end of the presentation. But maybe let's shift gears a little bit and talk about variational inference, which solves the same problem, but with a different approach. And the idea of variational inference is, once again, I'm going to approximate the target distribution. But what I'm going to do is I'm going to create this optimization problem where I define a family of tractable distributions. And within that family, I'm going to try to find the best approximation to my target by minimizing some objective function. Right? And so the nice thing about optimization is that there are a lot of people who work on optimization, notably in machine learning, and on running optimizations efficiently on GPUs. So we often do stochastic optimization for variational inference. And there's always this promise that variational inference might be a very fast alternative to MCMC for Bayesian analysis. I'm leaving a question mark here because, one, I think that the many short chain regime of MCMC changes that a little bit. And two, I want to talk about the quality of the approximation that variational inference returns and whether it's actually comparable to what you get with MCMC. There are a few design choices. First, I need to pick an objective function. So typically, people will minimize the Kullback-Leibler divergence, which simply compares log densities over measurable sets. You can also do these score-based divergences. So it's not the only possible objective function. And I'll talk about how different choices of objective functions affect your optimal solutions. And then you have to pick Q. So typically, people pick fairly restricted choices. For example, factorized distributions. That's called a mean field assumption. And that's in order to have, to really scale to high dimensions, or something even as simple as a Gaussian is often used in practice. And you can imagine that with these kinds of restrictions, you're never going to find an exact match for your target distribution. And my question is this a problem? How do these imperfections manifest? And do they actually stop us from doing inference and solving statistical problems or scientific problems? So I'll start with a positive result that we recently uncovered, which is that it turns out variational inference is very good at learning symmetries. And the result is the following. So I'm going to define something called even symmetry. And what that simply means is that there's some point, and if I take a point that is symmetric with respect to this point, the density stays the same. Right? So here, this is an example of a Gaussian, right? The Gaussian is even symmetric. And we have the following theorem that says that suppose your target distribution is even symmetric, and take as your family of approximation a family with a location parameter. Right? So a Gaussian, a student T, a Laplace approximation. Then, if you minimize the KL divergence, you will find that the optimal location parameter matches the mean. Sorry, not the mean, the point of symmetry. But it turns out that for a lot of distribution, that point of symmetry corresponds to the mean. So there are a lot of empirical observations that tell you that variational inference is good at estimating expectation values. And we may have a formal result that explains why that is the case. Now, the other thing that I want to highlight is how little conditions there are about what Q needs to do. All I'm saying is my target is symmetric, my approximation is symmetric, then the symmetries will be learned. But for example, my VI approximation could have a completely different tail behavior than my target distribution, or it could have a different factorization, right? So this is an example of a factorized Gaussian applied to a multivariate student T, so wrong tail behavior, wrong factorization, and I'm guaranteed to recover the point of symmetry, which in this case corresponds to the expectation. When we got this result, we were really trying to justify why variational inference is good at estimating expectation values. But then we thought, well, what are other symmetries that variational inference might be good at learning? So another natural symmetry that arises is this elliptical symmetry. And really what elliptical symmetry is saying I have some linear transformation that I can apply to my distribution such that it becomes spherically symmetric. So again, the multivariate Gaussian, right? If you apply the inverted Cholesky decomposition of the covariance matrix, you will recover a spherically symmetric distribution. So here's the theorem. Suppose my target is elliptically symmetric, and now I'm going to take a family of approximation. I'm allowing myself to optimize both the location and the scale of the distribution. Then it turns out that this target distribution, this approximation, by minimizing the KL divergence, learns the elliptical symmetry of my target distribution, right? And again, despite a certain number of misspecifications that I might have, such as tail behavior. So here's an example. Again, multivariate student T approximated by a multivariate Gaussian. My ability to learn the elliptical symmetry means that I exactly recover the isoprobability contours. All right, is there an interesting, statistically meaningful quantity that I'm actually learning? So one thing that I'll say is that you're not able to learn the covariance matrix of the target, but you're able to learn it up to a multiplicative constant, which means that you actually recover exactly the correlation matrix. And this was not a result that people were aware of. Variation inference is very good at learning correlation matrices, it turns out. Yes?
Sean, just a question. How close or how far are these two methods computationally? Meaning the variational inference and MCMC that you presented before.
Let's save that question for the end.
All right.
Let's save that question for the end, right? But the main difference right now is that on the one hand, I have a sampling method, and on the other hand, I have an optimization method. And optimization, a priori, all I'm solving for is kind of a bias. I don't have to worry about the variance. But thinking of the many chains regime, the two methods are a bit closer to one another. But let's talk about it then. Yes.
So I mean, most posteriors that I look at in my recreationally, obviously, have no point of symmetry and they have no elliptic symmetry at all. I mean, they're not Gaussian, they're not T. There are something really ugly usually.
Yes.
They don't have to be multimodal, but they certainly don't look like this. So what can I get then? And on the other hand, can't I get this with a Laplace approximation as well?
Yes. Okay. So that's a very nice question. So there's a sense that. So the first question is, when might I expect the posterior to be symmetric? And this is a little bit, content for future work, right? So it's worth thinking. So you could ask if I have a symmetric prior and a symmetric likelihood. Can this help?
Everything is Gaussian, yes.
That's true. That's true. Not always. The one thing that might be appealing is if you have a Bernstein-Von-Mies theorem that tells you that if you accumulate a lot of data, then your target starts looking Gaussian and therefore symmetric, right? So that's nice in regimes where you have a lot of data, which arise in machine learning, but it's not universal. So you're right, there are real limitations to this result. And in a way, I would say, if I think about, understanding, the relevance of variation inference, this is a bit of a first step in studying an algorithm that really lacks a lot of theoretical foundation, but it's not completely satisfying, right? It's a positive result to some extent. And with that, let me actually move on and share a negative result, by the way, about variation inference. And this is about factorized approximations, right? So now I'm assuming that all my variables are independent. And I'm going to ask the question, there's a bit of suspense because you can't tell what it's saying. But the question is, how good is variational inference at estimating uncertainty? And you may have read that variation inference does a poor job estimating uncertainty. And actually, one question I had when I read that is, well, how do people actually define uncertainty? Right? Which I know people here think about. So I want to, examine three measures of uncertainty. One is the marginal variances, one is the marginal precisions, and one is the generalized variance, which can be related to the entropies, at least in the Gaussian case. And what we were able to derive is a possibility theorem that tells you that a factorized approximation can learn any one of these measures of uncertainty, but you cannot learn two of these measures simultaneously. And to see that, so here's an example. So I have an elliptical Gaussian, which I'm approximating with a factorized Gaussian, and I've shown you the precision, the entropy, and the variance matching solution, and you can see that they're different. But geometrically, why might you expect them to be different? Well, if you look at the entropy matching solution, really what I'm saying is the volume of the sphere has to match the volume of the ellipsoid. And it turns out that setting the correlations to 0 increases entropy. You're increasing the volume of the sphere. On the other hand, if I want to match the variances, I have to match the axes of the ellipse. And because I've set the correlation to 0, I now have a sphere that has a greater volume than my ellipsoid. So the only way in which I can match the entropy is by shrinking the variance. And it turns out that there are a lot of examples where actually variation inference does a very good job estimating the entropy, which is kind of what it was used for in statistical physics. That's one of the original motivation. But because of the impossibility theorem, it means it does a poor job estimating the variance, which is oftentimes what we care about in Bayesian statistics. Now, a natural question is, how does variational inference resolve that impossibility theorem? And it's going to depend on your choice of objective function. So we've spoken about the Kullback-Leibler divergence. There are just other divergences which also essentially compare log densities. So you have this Rényi divergence, which is really a generalization. And then you have these score-based divergences, which are going to compare gradients. All these are valid divergences in the sense that they're always positive and they're equal to 0 if and only if you get exact match between the densities. But it turns out they give you very, very different solutions. So here again, in the case of the Gaussians, you can see which divergence matches the variance, which one matches the entropy, and which one matches the precision. Right? And you can also just visually see that all those solutions are quite different. So one thing we were able to show is that there exists an ordering between these divergences based on any measure of uncertainty, how much uncertainty they assign to an optimal solution. This is an ordering you can prove exactly in the Gaussian case, and that empirically, we find holes on non-Gaussian targets. You can find, in this case, a variance, an entropy, and a precision matching solution. And now something that we did not quite expect is that when we looked at those score-based divergences, we actually found cases where the optimal solution, the optimal variance collapses to 0. In other cases where the optimal solution blows up to infinity. So somehow these divergences, which look pretty harmless, it turns out that if you analyze them and you throw them at some simple case, can fail in a spectacular fashion. So some outlooks on variational inference. So first of all, we spoke about symmetries, and I think the question to ask is, what are other symmetries out there that variational inference might be good at learning, and how do these symmetries correspond to inference tasks that we're interested in? And then another case, suppose I'm in a situation where my target is not exactly symmetric, maybe approximately symmetric. Can I nuance my theory so that instead of getting exact recoveries, right, I can have some kind of error bound? So that's a natural next step. Impossibility theorems. So studying, precisely the impossibility theorem in non-Gaussian cases. So what makes the Gaussian case complicated is that even though the KL divergences are fairly easy to analyze, all these other divergences quickly become complicated. You no longer have access to analytical solutions, but you can still do some really nice math to get some results. But of course, we care about non-Gaussian cases. What are useful ways to generalize this theory? And then this idea of an impossibility theorem, that's actually a very good way of characterizing the cost you pay whenever you do an approximation, right? For example, if I approximate an asymmetric distribution with a symmetric distribution, I'm going to expect an impossibility theorem between the expectation value and the median. Right? So it stands to reason that this impossibility theorem framework is quite a bit more general. So I want to conclude with a bit of a bigger picture, which is, my goal is how can we do fast and reliable inference with parallel computation? And that was the topic. We spoke about Markov chain Monte Carlo, the many short chain regime of MCMC, the convergence diagnostic nested our hat, which really enables a practical use of the many short chain regime. And of course, one of our long-term goals is to build an adaptive warm-up length. But one thing that's going to matter with the adaptive warm-up length is going to be what is the precision of the Monte Carlo estimator that we want. But we're not trying to drive the bias to 0. That's too expensive. We're trying to drive the bias below a certain tolerance threshold. And now suddenly scientists are going to have to worry about, well, what bias are they willing to tolerate? What variance are they willing to tolerate? And this is going to be a whole new conversation to start with scientists about Monte Carlo precision. But I'd rather have this conversation than some debate about how long the Markov chain should be or what effective sample size I should have. Because even in that debate, hidden implicitly is the conversation about the precision of Monte Carlo estimators for scientific applications. There's another thing which is as great as GPUs are, there are some operations that are very difficult to perform on GPUs because they end up not all being the same across threads. For example, solving differential equations, when you use certain kinds of integrators, what ends up happening is the number of steps that the ODE solver takes varies depending on where you are in the parameter space, which means it's difficult to synchronize those operations on GPUs. So if we can move from these classical integrators to surrogate models, for example, you learn a neural network to solve the ODE, well, neural networks we can run efficiently on GPUs. So I think these surrogate models are going to play a big role. Variation and inference. So here, developing some theoretical guarantees. So we talked about symmetry guarantees, also impossibility theorem for uncertainty. But of course, if you want to move past the impossibility theorem, if you want to move past symmetric distributions and tackle the kind of distributions that arise in the wild, why not use a richer family of approximation? And I have some very recent work with some colleagues where we've developed semi-parametric variational families, which kind of work like a function expansion where the first term is a Gaussian, and then every term you add allows you to model non-Gaussianity. But the computational cost grows very quickly once you start using expensive variational families. And what we have found is that these score-based divergences, which fail so spectacularly when you're using a restricted approximation or factorized approximation, actually give you very nice optimization problems once you use richer families. But of course, this is a bit of a tuning problem, right? How do I pick the richness of my variational family? And this is, something we want to spare to the scientist who's analyzing the data. So is there a way to construct adaptive variational families that can at once be expressive enough, but also allow me to control the computational cost? And this idea of gradually increasing the complexity of my approximation, not necessarily to get a perfect match, but to get a match that's good enough for all the inference tasks that I'm trying to perform, right? And going back to Michael's question, when you think about evolving distributions that evolve from something initial to something that gets maybe closer to your target distribution, suddenly it starts resonating with MCMC. When I look at only decreasing the bias and no longer the variance, suddenly this starts looking more like an optimization problem. So I think we're going to find in the future that these two classes of algorithms are actually more profoundly connected than they currently are with existing